episode 96. We are almost done. This is part 6 of 7 on our series on what raises and lowers given chemistries in a swimming pool. And today, we are going to talk about what raises and lowers combined chlorine. Now, we cover combined chlorine in more detail in episodes 16, 30. The main two are 32 and 33, but also 37, 63, and 76. How to raise and reduce combined chlorine. So let's get right into it. Episode 96 of the Rule Your Pool podcast.
Welcome to Rule Your Pool, the podcast by Arenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go.
Combined chlorine is a measurement of chlorine that has combined with nitrogen compounds. It's usually ammonia or urea, and we measure this by subtracting free chlorine from your total chlorine. Okay, so the difference between your free chlorine and your total is your combined. You don't want any. Most health codes have a limit of 0.5 parts per million, but a recommended threshold of 0.2 parts per million. If you have any combined chlorine in your water, your real question is, where did the nitrogen come from? Or more importantly, if it's still happening, where is it coming from? Is it a continual source of nitrogen, or was it a one-time event? If you have combined chlorine in your water, you have nitrogen in your water in some form. It is best to find out where that came from and address that, rather than trying to address combined chlorine on its own without focusing on the source, because it takes a lot of chlorine to handle this unless you have other systems in place. When chlorine combines with a nitrogen compound, it's part of the oxidation process. This is how you have to get nitrogen out. And while this is occurring, these compounds that have chlorine combined to them, they actually do have some minimal disinfection power. But I say minimal, like monochloramine is sometimes in drinking water because it does have some disinfection power, but it's so much slower than hypochlorous acid that it allows chlorine to go all the way through the municipal piping system all the way to your house. So it slows chlorine down intentionally. So a lot of drinking water now is chloraminated. Not chlorinated, chloraminated. That can be a problem. So just be aware of that. And in order to destroy this, chlorine combines with it, and you have to get to a threshold where you can get past the nitrogen demand and create a free chlorine residual. That process is called breakpoint chlorination. And now that I'm thinking about it, I just scrolled through all of our past episodes. I don't think we've actually done an episode on breakpoint chlorination. I should put that in the queue. Should probably do 2 or 3 episodes on that, because that's a very good topic, in particular for commercial swimming pools. So, what causes combined chlorine to increase? What puts it in your pool? Well, as I already mentioned, nitrogen. So let's talk about the sources of nitrogen. The first thing is your tap water. You may have nitrogen that was deliberately put in the tap water by your city drinking water facility to get chloramination so that you can get monochloramine into your drinking water and disinfect over long distances of plumbing. That's becoming more and more common. So when in doubt, check your tap water. That would be the first thing you should test. Then let's talk about sources of nitrogen that are local to you. If you have an outdoor pool, it could be from decaying organics. It could be from leaves, grass clippings, fertilizers, soils, etc. Things like that contain nitrogen in them because they're living things. They also contain phosphates. They also contain carbon. They also contain tannins. But nitrogen is one of those things. You also get urine and urea from bathers or dogs. So I was a swimmer. Swimmers do pee in the pool. As gross as it is a reality. We have to deal with it. In a swimming pool with a swim team, let's say you've got 40 or 50 people in the pool training for 2 hours. It's not in the swimming culture to get out in the middle of practice and go use the bathroom. Although it should be, it isn't. The reality is you'll lose your warm-up. You will get cold when you get out of the pool. Evaporative cooling on your skin's a real thing. It's so bad that you can get out and it could be 84 degrees on deck and your teeth could shatter because it's so cold if you're, under the air conditioning with the air moving. But that's a topic for another day. The point is, swimmers don't often get out. But we know that the levels with a full swim team training in there, for multiple hours a day, they're not really going to get over half a part per million. So if you have really high levels, and when I say really high, I mean over 1 part per million of combined chlorine is what I would consider really high. It's almost always a chemical source of nitrogen, not just people. Ammonia is getting into that pool somehow. Now, in commercial pools, the first place you should look is deck cleaners. Any cleaning products around your pool that contain ammonia, they are going to directly contribute to your combined chlorine. We were called into an indoor water park a few years ago, and they had 7 bodies of water. 4 of them had awful combined chlorine, like over 3 parts per million. Super high, like health department shutting them down high. But the other 3 bodies of water were fine. They had like 0.2, which is expected in a busy water park. What was the difference between those 4 and the other 3 bodies of water? Well, we couldn't figure it out. Long story short, it was the deck cleaner. The deck cleaner in this floor cleaning Zamboni machine was dimethyl ammonium chloride. And that cleaning product was being driven around disinfecting the deck, because dimethyl ammonium chloride is an awesome sanitizer, but they were driving over the gutter of these 4 pools. The 3 pools that did not have the issue had rope fences around them so the Zamboni couldn't get to the gutter. And it was just like the most obvious aha moment. Like, wait a second, this was just the deck cleaner. So we had the client call the chemical supplier, replace it with a non-ammonia-based deck cleaner, and the problem went away in like 2 weeks. It was great. So always look around and say, hey, let me look at the ingredients of my chemical to make sure it does not contain ammonia. If you don't know, ask. You can Google every product. You can find their SDS sheet. It'll tell you if there's ammonia in it. And if you don't know what an ingredient is, ask someone who is more in tune with it, or ask us. Send us a picture of it to podcast@arendatech.com. So that's it. Decaying organics, tap water, bathers, and ammonia products. Now that's commercial, like deck cleaners, cleaning products, all that. In residential pools, the number one source that we have found is algicides. A lot of algicides are ammonia-based. Ammonium sulfate, ammonium chloride, dimethyl ammonium chloride, or quaternary ammonia. So if you have a quat in the name of your algicide, quat stands for quaternary ammonia. That will contribute to your combined chlorine, and it takes a lot of chlorine to get rid of that. Now, one other thing is eventually cyanuric acid will break down into uric acid, which, I'm paraphrasing here, breaks down into ammonia eventually, and it takes a lot of chlorine along the way to do that. So if you have CYA that is breaking down over time, which it will, that is going to contribute to your combined chlorine. Generally speaking, though, if you do what we recommend anyway and you stay below 50 parts per million at any given time, it's not going to be a very noticeable number. So that should not be a big contributor. Nothing like ammonia-based cleaners or algicides would ever be. All right, so now that we've covered what contributes to combined chlorine, meaning nitrogen sources, how do you get rid of them? How do you decrease this? Well, if you go back to our podcast, we go in depth on this in episode 33. It's pretty much an entire episode where Joe and I talk about how to reduce combined chlorine. And in that episode, Joe and I broke it into 2 categories of removal: chemically removing it and mechanically removing it. The chemical ways to reduce this, let's start with breakpoint chlorination. We'll do a few episodes in the future on what that specifically means, but we'll just call it superchlorination. The general rule of thumb is 10 times your combined chlorine in free chlorine should destroy it. Now, technically, that's more than you actually need, but 10x will definitely get the job done, or at least it should. If it doesn't, you probably have a different source of nitrogen that is overwhelming what you're doing, and you should probably reach out to us so we can help you figure that out. Now, superchlorination will oxidize the inorganic chloramines, meaning monochloramine, dichloramine, and trichloramine, but it may not be able to fully oxidize the chloroorganic compounds. They're more complex, and there's hundreds of variations of these things. Chlorine will oxidize it and reduce it down to whatever it can, usually down to like nitrates and something. But generally speaking, you can't 100% get it out of your water. But as long as you get past the break point, you can hold a free chlorine residual, and that's what's important. You can also use a non-chlorine shock like potassium monopersulfate. We did some research on this because, to be honest, I'm not that familiar with potassium monopersulfate. I'm not an expert on it. But according to Taylor Technologies, potassium monopersulfate will not actually oxidize already formed combined chlorine directly. It will oxidize the precursors to it, meaning it'll oxidize the nitrogen compounds provided they have not yet combined to chlorine. So you can use it. It's an awesome shock. You don't want to use it a lot, but it will absolutely help reduce the nitrogen demand on your chlorine. And the final chemical way to do this is to use enzymes. Although I want to be very clear, enzymes do not reduce the amount of nitrogen in your water. They don't do anything to nitrogen. What they will do is help break down these more complex chloroorganic compounds. So we got inorganic and we have organic. The inorganic would be pure ammonia, basically. When pure ammonia, NH3, combines with chlorine, you get a monochloramine. And then at a 5-to-1 molar ratio on top of that, you get a dichloramine, meaning another hydrogen's been swapped with a chloride. And then you get a trichloramine, and that trichloramine is what off-gasses, and that is the pool smell. As a swimmer, swimming for 10 years indoors gave me permanent lung scarring. It's actually the main reason I'm in the industry is because of this issue. I am intimately familiar with what trichloramines do. They're brutal. You got to get them out of your water. But mono, di, and trichloramines are inorganic chloramines. The organic chloramines contain carbon. They're a lot more complex. These are more complex bather wastes and things that are contributed with like sunscreen and stuff like that. Those precursors, those nitrogen compounds, can be broken down somewhat by enzymes. Only the carbon parts, though. It won't touch the nitrogen, but you can at least simplify and break down this complex chemistry so that when chlorine does combine with it, it's really focused on the nitrogen itself and not having to burn through all of it. So to be clear, enzymes do not touch the nitrogen. They simplify the compound so that it takes less chlorine to actually destroy it. It's still chlorine that's reducing the combined chlorine. It's just taking less chlorine to do it. Go into my head. It made sense when I said it. And, I actually do have show notes, but it's just a few bullet points. So I should have probably gone into more depth on that. But if you have questions on that, reach out. Now let's talk about the mechanical ways to reduce combined chlorine. Now there are some advanced filtration media these days that are claiming to reduce combined chlorine. And so far, mixed reviews at best. But the reason I'm bringing that up is because it's showing promise in that technology is developing. Hopefully one day soon, there will be filtration techniques that can reduce combined chlorine directly. So far, I don't think we're quite there, but I think we're getting pretty close, and that is very exciting. But for now, the mechanical ways to do this is with a secondary system. So we'll break this down into secondary oxidizers and UV. We'll start with UV. There are two different types used in pools. Low pressure, which is common in low-use commercial pools and residential pools. Low pressure UV can destroy monochloramine. Now UV is not an oxidizer, so it can't destroy the precursors. It can't destroy the nitrogen compounds. But once that compound has combined with chlorine, UV can destroy that compound. It can destroy the combined chlorine, but it can't destroy or oxidize the precursors. And then you got medium pressure, which can destroy not just monochloramine, but also dichloramine and trichloramine. And the limiting factor with UV is that it is a point of contact system, meaning it can only destroy what goes through its chamber. It can't reach out into the pool and destroy everything. This is completely at the mercy of the circulation rate and the circulation system. If you don't have a good design, you have dead spots in your pool, it's not going to be able to get that water. Same could be said for secondary oxidizers. The main one is ozone. Another one is AOP, advanced oxidation process. I'm going to lump these two together because they're both very effective if they're installed correctly and delivered right. They will destroy just about everything. They're great sanitizers, but they're really good oxidizers, which means ozone and AOP, they don't just destroy the combined chlorine. They'll destroy the precursors, the nitrogen compounds, the chloroorganic compounds. They basically destroy everything we're talking about in this conversation. The weakness is they're also point of contact. They are both completely dependent on the circulation rate of the pool. That's their weakness. One final note. Eventually, after all of this nitrogen is oxidized, it's not like it leaves the pool completely. You can't 100% remove it from the pool, unfortunately. It usually gets boiled down into a nitrate. And a nitrate is the final stage of nitrogen where it cannot be oxidized any further. Unfortunately, nitrates are food for algae. So you need to be aware of that. And, at low levels, they're not really a problem. They're kind of inevitable. But if you have a lot of them, the only way to get them out of your pool is to drain and dilute or reverse osmosis filtration. So anyway, that's episode 96. For more detail on reducing combined chlorine, go back and listen to episode 33. I'm your host, Eric Knight with Orenda. This is the Rule Your Pool podcast. This is part 6 of 7, which means there's only one more to go. We'll see you next week. Thank you for listening.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.